So next, force on dielectrics. So what is the force acting on a dielectric when it is subjected to an electric field? That is our next discussion. Just imagine a linear dielectric slab. This is the linear dielectric slab. It is kept in between two parallel plates. The first is connected to the positive terminal and next is connected to the negative terminal, so that a uniform field is acting in between these two plates, and the plate's length is W and width is A, and they are separated by a distance D. And in between these two plates, this linear dielectric slab is slowly pushed inside. So what happens is, when this slab enters in between these two plates, the uniform field, it fringes, it bends like this, fringes. So fringing field is produced where the slab enters in the space between the parallel plates. So slab is introduced partially between the plates of a parallel plate capacitor, and the field inside is uniform and outside the plates the field is zero. So for bringing this slab inside this space, so we are applying a very small external force, F external. So due to the application of this F external, energy is changed. That is, energy is dW, change in energy is dW. And due to this F external, the displacement produced is ds. So we get the equation dW equal to F external into ds, equation number 1. So F external is in this direction. At the same time, the fringing field exerts an equivalent force in the opposite direction. This equivalent force is capital F. These two are equal and opposite. So F external is equal to minus F. So we got two expressions. F external, dW equal to F external into ds, first equation. Second equation, F external is equal to minus F. So what would be the value of dW? dW becomes, instead of this, minus F into ds. So the electrical force in the slab, F becomes, F is equal to minus dW by ds. That is equation number 3. Then we have to calculate what is the value of W, and by getting the value of W, we have to differentiate it with respect to the distance mode. So energy of a capacitor is W equal to half CV square, but this also can be written as half Q square by C. That is V equal to Q by C. Substituting V equal to Q by C. So V equal to Q by C becomes, so V square equal to Q square by C square. C and C are getting cancelled. Then, so equation number 3 can be rewritten as F is equal to minus dW by ds. It can be written as dW by dc into dc by ds. So that dc and dc are getting cancelled. Again, we are getting back this dW by ds. So this F is equal to minus d by dc of this first one. W, instead of W, half Q square by C is written here, into dc by ds is written here. So this this is a dc is then differentiating this with respect to C, we are getting this term, and dc by ds is here. So minus of minus my Q square by 2c square into dc by ds, equation number 5. So this is half is taken outside, minus into minus plus, half Q square by c square into dc by ds, equation number 6. Put Q by c as V again. So F is equal to half V square dc by ds is equal to number 7. So we are getting number 7 just like this. In this we have to find the value of the dc by ds. To find dc by ds, here we are considering the two parallel plates, and these parallel plates is in the figure. The parallel plates acts as two capacitors. I have already said two capacitors C1 and C2, and first one is an air capacitor, air as dielectric, air capacitor, and its width is W minus S, total width W, and W minus S is the air part, width of the air part, and it is multiplied with the breadth A, so we are getting area. So then second one with dielectric, its a length is S and breadth is A, so area is SA. So we got the equation for the parallel plate capacitor C equal to epsilon 0 A by D. So here for the first one, this A is this one, this is our area. So epsilon 0, this area by D, same, D is same for both. And the second one, area is SA. And so this is the total effect. But instead of K, we can write epsilon R equal to chi E plus 1, susceptibility plus 1. We have already studied this. So substituting this, the equation above becomes C is equal to epsilon 0 W minus S into A by D plus epsilon 0 chi E plus 1 by D SA. So equation 8. And substituting the value of C and using this equation 8, we can find dc by ds, differentiate C with respect to S. So this becomes epsilon 0 A into minus 1 by D plus epsilon 0 chi A by D plus epsilon 0 A by D. So we are getting this equation. Substituting the value of dc by ds in equation number 7, we are getting this equation. And finally, half b square dc by ds, the value of dc by ds is equation number 9. So this is the value of the dc by ds. And finally we are getting the force F is equal to half v square epsilon 0 chi A by D, where F is the force experienced by the dielectric slab in between when it is moved, when it is pushed with a force F external to inside to a distance S inside. Okay, so this gives the force. Now we think about the case, and these parallel plates, they are connected to a battery. And so potential V remains constant. So charge changes. So when it is connected to a battery, its charge is changing. Due to the change of charge dq, an energy is developed here. So dW, new energy, dW will be V dq plus F external ds, F external ds. So we know F external is equal to minus F external equal to minus F. So we can write plus F external equal to minus F. So this becomes dW equal to V dq minus F ds. So V dq, what is this V dq? V dq is the work done by the battery when charge changes by dq, when it is getting charged. From this 11, we can say F ds is equal to V dq minus dW. V dq minus dW. And so from this F is equal to V dq by ds minus dW by ds, equation number 12. And we know Q equal to CV, substituting. So what is this? dq by ds. dq by ds can be written as Q is equal to CV, so V into dc by ds. We know the energy W is equal to half CV square in the case of a capacitor. So dW by ds, dw by ds, this dw by ds is equal to half v square dc by ds by differentiating this with respect to s. So you are getting 40. So we are getting two differential equations, that is 13 and 14. So substituting this 13 and 14 in this equation 12, we are getting f is equal to v square dc by ds minus half v square dc by ds. And this f equal to, therefore f is equal to half v square dc by ds, equation 15. So 9 changes to, equation number 9 changes to dc by ds is equal to epsilon 0 chi a by d. Substituting in 15, we are getting f is equal to half v square epsilon 0 chi a by d, that is 60, equation 60. We know force is not depending on q. You see, there is no q factor here. So the charge is not in this equation. So force is not depending on charge q. Also, we know chi e, susceptibility is k minus 1. K is equal to epsilon r. And we know V is equal to V, D, V is the PD, E applied a electric field, D is the distance between plates. Then F equal to, then from this substituting these values in this equation, we are getting epsilon 0a by 2d into ED square by into chi. So finally, we are getting epsilon 0a E square d by 2 chi, equation 70. So this equation 17 represents the electric force acting on the dielectric medium between capacitor plates. Also we know epsilon 0 chi E equal to P, the polarization vector P. This is P, we have studied that. So substituting for this epsilon 0 chi E, epsilon 0 chi E, so epsilon 0 chi E, instead of this you are substituting P, so we are getting the equation F is equal to PEAD by 2. So finally F is equal to half PAV is the force acting on the system. That is F is equal to half PAV, where P is the polarization and the A is the distance and V is the PD. V is the PD. Relation between polarizability alpha and the susceptibility chi of a dielectric medium. We have the equation polarization equal to P equal to epsilon 0 chi E. Chi is the susceptibility. E electric field, epsilon 0 permittivity of free space, P polarization. If the dielectric medium consists of non-polar molecules, each molecular dipole will have electric dipole moment P. So P is the electric dipole moment. Then P is equal to alpha E. We have studied this equation earlier. P is equal to alpha E, where alpha is the polarizability. Also, the polarization P equal to N into P, where N is number of dipoles per unit volume. Number of dipoles per unit volume. And the small p, it is the dipole moment. So substituting 2 in 3, this is equation number 3. 2 in 3. We get P equal to N into alpha E. Okay, but P is equal to epsilon 0 chi E. Substituting for P, you are getting this equation. Epsilon 0 chi E equal to N alpha E. From this, chi E can be calculated as chi E is equal to N alpha by epsilon 0. N is the number of dipoles per unit volume. Then alpha is the polarizability. Epsilon 0 permittivity of free space, 854 × 10⁻⁻12. And from this, you can calculate the susceptibility of the medium. And so this is the relation between the polarizability and susceptibility of the dielectric. We are considering a special case, that is the dielectric medium is having very high density. That is capital N is very large, number of molecules per unit volume is very large, and we are considering non-polar molecules, not polar molecules, but it is non-polar molecules. Here we are getting a final equation. That final equation is called Clausius-Massotti equation. So for this, we have to consider high density. In our topic, it is very high density molecule. That is, molecules are very close to each other. So you just see this figure. If you consider this blue, this is the dielectric medium, and the dielectric medium is having its own electric field, that is ELs. And you imagine here a sphere of radius r, and this sphere of radius to each molecular dipole is assigned a radius r. You just simply an imagination. So this molecule is having an electric field which is called E self, and outside this molecule the dielectric medium is having a field that is ELs. So that the total electric field is E self plus ELs. So E self is due to polarization of the molecule, and the ELs is the external field. And here molecular density N is equal to 1 by 4 by 3 pi r cube, where r is the radius of this assumed, this imagined molecular dipole sphere. And the P is having the usual equation epsilon 0 chi e. And the induced dipole moment in the molecule is dipole moment of P, alpha polarizability ELs. This is equation number 4. And here, inside this sphere, the polarization capital P is equal to N into small p, where small p is the dipole moment. And substituting 4 in 5, we get P equal to N into alpha into ELs. So from this equation, ELs is equal to minus P by 3 epsilon 0. Minus P by 3 epsilon 0, which is equal to minus N alpha ELs by 3 epsilon 0, equation 8. Substituting this equation 8 in 3, which is 3, this one is 3. The resultant electric field E is equal to N alpha ELs by 3 epsilon 0 plus ELs. So ELs into 1 minus N alpha by 3 epsilon 0 is there. So ELs is equal to E by 1 minus N alpha by 3 epsilon 0. That is equation 9. So here we got ELs and ELs in equation 9 and the E self in equation 7. So substituting in 6, we get a polarization vector P equal to N alpha by 1 minus N alpha by 0, equation 10. Comparing equation 1 and 10, 1 is P is equal to epsilon 0 chi E. Then comparing these two equations, we are getting epsilon 0 chi E equal to this much. From this, epsilon 0 chi E is equal to N alpha by 3 epsilon 0 minus N alpha by 3 epsilon 0. And from this, we have to calculate chi E. Chi E is equal to 3 N alpha by 3 epsilon 0 minus N alpha, that is equation 11. Cross multiplying, then this term goes to LHS, so this becomes 3 N alpha. And from this, we are calculating chi E. And the chi E becomes N alpha into k plus 2 by 3 epsilon 0, equation 12. And here, the relation between k and chi E is considered. Chi E is equal to k minus 1, and it is converted into chi E. So this chi E is equal to k minus 1 we have substituted. Then chi E is equal to so much. So this is the relation between chi E and alpha. That is the susceptibility and polarizability. So this relation holds good for very high density molecules. Very high density molecules. And this equation 12 is the relation between chi E and alpha. From this, also we can write k minus 1 is equal to so much n alpha, this one. From this expression, k minus 1 equal to n alpha into k plus 2 divided by 3 epsilon 0. And from this, alpha can be determined as alpha equal to 3 epsilon 0 k minus 1 divided by n into k plus 2. And this equation is known as the Clausius-Massotti equation. Clausius-Massotti equation. Okay, thank you for listening to me. And here we are completing the 4th semester syllabus. And then in the next class, we will continue in the 5th semester syllabus of electrodynamics. Okay, thank you.